This is video 23B for the Year 9 Mathematics course. In this video, we're going to cover the theory behind the trigonometric ratios under the topic of trigonometry. Specifically, we are going to explore the trigonometric functions sine, cos, and tan, the trigonometric ratios, also known as SOHCAHTOA, the tangent identity, the trigonometric Pythagorean identity, and then we're going to cover some example questions. Alrighty, so in our last video, we introduced this idea of trigonometry, and effectively how at this point in time we're going to be using trigonometry on right angled triangles to solve for missing side lengths, but we can also use it to solve missing angles. So what we're going to be looking at today is going to be the next step towards how we use this idea of trigonometry to solve for these missing quantities. And what we're going to be looking at today is something called the trigonometric ratios. Now, in order to go through these ratios, we're first of all going to do a quick bit of revision on what we also looked at in our last video on the important terminology when it comes to the three sides of any right angle triangle. So, when we have a right angle triangle with the right angle occurring at that point there, we know that the side which is directly opposite the right angle is called the hypotenuse. And if we provide a reference angle theta in this position here, then we know that the opposite side is the side, as the name suggests, which is directly opposite the angle theta. So for this particular right angle triangle, this one here would be the opposite. And then the side which is adjacent, or in other words, next to the reference angle theta, is what we call the adjacent side. Now, I'm going to leave this up here just for now, purely because we will be using these three pieces of terminology quite a bit over the next few videos. So as I was making mention of it in our last video as well, if you're still a little bit unsure about how to clearly identify the hypotenuse, opposite, and adjacent sides of any right angle triangle, probably a good idea to go back and do that before proceeding with the rest of this content here. Now, what I would also like to do here is unravel a mystery that you may have been pondering over these last few years, and this is to do with three very important buttons that you've probably seen on your calculator quite a bit, but have had absolutely no idea what they are or what they're used for. And the three buttons I'm talking about are the one that is spelt S-I-N, the one that is spelt C-O-S, and then the last one which is spelt T-A-N. Now, this first one here is pronounced as sine, not sin, sine. This next one is pronounced as cos. And then this last one is pronounced as tan, so pretty much exactly how it's spelt. So, what are these three things here? Sine, cos, and tan. Well, what these are parts of what we call the three key trigonometric ratios. And what are the trigonometric ratios? Well, they are effectively a means of how we can connect the three sides of any right angle triangle using equations. What do I mean by that? Well, here are the three trigonometric ratios. First things first, we say that sine of the angle theta is equal to the opposite divided by the hypotenuse. We also have that cos of theta is equal to the adjacent divided by the hypotenuse. And finally, we have tan of theta is equal to the opposite divided by the adjacent. Now, just as a quick side note, oftentimes when we're writing these three trigonometric ratios, we don't bother writing the entire names of opposite, adjacent, and hypotenuse as we've done here. What we often do instead is we just abbreviate these to the first letters of each word. So the hypotenuse gets abbreviated to a capital H, the opposite gets abbreviated to a capital O, and then the adjacent gets abbreviated to a capital A. So for these three trigonometric ratios, we would say that sine of theta is equal to O divided by H, cos of theta is equal to A divided by H, and then tan of theta is equal to O divided by a. Quick bit of terminology here as well. When we have these three things here, we use the phrase sine of theta, cos of theta, tan of theta. So in other words, sine of the angle, cos of the angle, tan of the angle. Alrighty, so a few important points about these three trigonometric ratios. First things first, let's actually talk about these three things of sine of theta, cos of theta, and tan of theta. Now, what you can effectively think about sine, cos, and tan being, they're almost like functions. What I mean by that is, depending on the value that you substitute in for theta, whether it be 1 degrees, 2 degrees, 50 degrees, 60 degrees, or whatever, when you then put in sine, cos, or tan of the angle that you then consider, you're going to get a wide range of answers when you pop this into your calculator. So what I mean by that is, let's say we considered sine of 10 degrees or cos of 10 degrees and tan of 10 degrees. Then if we evaluate these to two decimal places each, sine of 10 is 0.17, cos of 10 is 0.98, and then tan of 10 is 0.18. Now, when you do pop these into your calculator, what you should hopefully notice is that these are what we call irrational numbers, as in, these numbers more or less just keep going on and on and on forever. So when we're working with sine, cos, and tan, oftentimes we get some very, very disgusting answers when we pop them into our calculator. There will be certain situations in which we actually do get some nice rational answers. So for example, if you were going to consider sine of 30 degrees or tan of 45 degrees, you actually find that sine of 30 degrees is equivalent to 0.5 and that tan of 45 is equivalent to 1. So these answers here, obviously quite nice. These answers here, obviously not so nice. However, it is very important to understand that these situations here, where we get some very disgusting numbers, are much more prevalent than in these situations here, where we get some nice, rational answers. The point that I'm trying to make here is that 99% of the time, when we're working with sine, cos, and tan, there will be some rounding and approximation involved because we're typically working with disgusting, irrational numbers. The other quick thing I wanted to point out here as well, which is a very, very important thing to understand at this point in time, is that sine, cos, and tan all by themselves are completely meaningless. What I mean by that is, if you open up your calculator and you put sine or cos or tan all by themselves into your calculator, then you're going to get no answer, because sine, cos, and tan by themselves do not mean anything. Sine, cos, and tan only mean something when we attach a number alongside of it. So again, sine of 10, cos of 10, sine of 30, tan of 45, and so on. So this is a very important thing to understand at this point, that when we have sine of theta, cos of theta, and tan of theta, these three things here are effectively representing some number that you can then evaluate using your calculator. And so that's all we're really going to be focusing on in this particular video here, just simply memorizing these three trigonometric ratios that says that sine of theta is equivalent to the opposite divided by the hypotenuse, cos of theta is equal to the adjacent over the hypotenuse, and then tan of theta is equal to the opposite over the adjacent. Now, of course, we are going to be using these three trigonometric ratios quite extensively over the next few years, so over time you will be able to remember these equations much easier as time goes on. Just like anything in maths, the more you use them, the easier it will be to commit to memory. However, I'm also very conscious of the fact that when you're first looking at these three equations, it can be very daunting to know that you're going to have to memorize these at some point, especially when it comes to the fact that we're effectively just getting different combinations of the opposite, adjacent, and hypotenuse side lengths. So the nice thing about these three ratios is that we've actually been able to develop a very, very nice acronym that helps us remember how we construct these three equations. So let me just quickly write out the three ratios again. So we've got sine of theta is equal to the opposite divided by the hypotenuse. We've got cos of theta is equal to the adjacent over the hypotenuse. And then we've got tan of theta is equal to the opposite over the adjacent. Now, the acronym that we're going to use to help commit these three ratios to memory, and just as a quick side note as well, even as someone who's been studying this stuff for 10 plus years at this point, I still use this ratio just because it makes my overall work significantly easier as well. So the acronym that we're going to be using is what we call SOHCAHTOA. Say it with me. SOHCAHTOA, SOHCAHTOA, SOHCAHTOA. My suggestion right now is to actually write down this acronym 10, 20, 30 times over. Say it to yourself again and again and again. And if anything, remember this acronym here rather than trying to remember the three trigonometric ratios, because it's much easier to commit the acronym to memory than at this point trying to commit the ratios to memory. Now, what does this acronym here actually tell us? Let's have a look at the first one, SO. The first letter is S, which tells us that we're going to be working with sine. The second letter is O, which tells us that the numerator will be the opposite. And then the third letter is H, which tells us that the denominator of the fraction will be the hypotenuse. So in other words, sine of theta is equal to the opposite divided by the hypotenuse. Let's move on to the next one, CA. The C tells us that we're going to be working with cos. The A tells us that the adjacent will go on the numerator. And then the H tells us that the hypotenuse will go on the denominator. So in other words, cos of theta is equal to the adjacent divided by the hypotenuse. And then last but not least, the capital T for TOA means that we're going to be working with tan. The O tells us that the numerator will be the opposite side. And then the A tells us that the adjacent will be on the denominator. So in other words, tan of theta is equal to the opposite divided by the adjacent. SOHCAHTOA, SOHCAHTOA, SOHCAHTOA. Try to commit this to memory sooner rather than later. The next couple of videos that we're going to be looking at will be all about how we use these three trigonometric ratios to solve for missing side lengths and missing angles. So we need to make sure that we can very easily write out these three trigonometric ratios using the acronym SOHCAHTOA. So this right now is going to be your prime opportunity to commit this to memory and make sure you understand how to use these to write out these three equations here. Alright, before we get into some example questions, there are a few more quick bits that we need to get through, mainly in terms of actually proving some very, very helpful trigonometric identities. However, before we do that, just as a quick side note as well, if you ever want to square one of these three ratios, so for example, if we wanted to get sine of theta and square it, as in sine of theta all squared, then the other way that you may actually see this written is sine squared of theta. So these two things here mean the exact same thing. Never try to put this into your calculator because it just won't actually compute anything. But whenever we're going through questions and working out, we'll typically see this kind of notation here. But this is what you would put into your calculator. And I'm sure you can probably guess why we do not use this kind of notation here, because what this here would imply is that the only thing being squared is the theta. So we do not want to use the squared purely on the outside of the theta. Alrighty, what we're going to quickly do now is actually go about using these three trigonometric ratios to prove some very, very, very important identities when it comes to the topic of trigonometry. And these are things that are going to pop up quite a bit over the next few years. So understanding how to prove these identities now will be a very, very valuable skill. The first identity that we're going to consider is once again one of the most important connections when it comes to the topic of trig. And that is that tan of theta can also be represented as the quotient of sine of theta and cos of theta. Let's see if we can now actually use the trigonometric ratios to prove this identity. So what we're going to do here is we're actually going to start off with the quotient of sine of theta divided by cos of theta. Because we know that sine of theta using our trigonometric ratios is equal to the opposite divided by the hypotenuse, and that cos of theta, again using our trigonometric ratios, is equal to the adjacent divided by the hypotenuse. So what do we have here? We have the fraction O divided by H divided by the fraction of a over h. This here is equivalent to O over h multiplied by h over a. Here, this h and this h are going to cancel each other out. So now we just have O divided by a, and we know that O divided by a is equivalent to tan of theta. So in other words, we've just proved here that tan of theta is equal to sine of theta divided by cos of theta. At this point in time, this identity isn't going to be super useful for the work that we're going to be doing, but trust me when I say that in future years, this is going to be very, very, very critical. Alright, the second identity that we're going to go about proving, and again, this is a very, very important one that we're probably not going to even end up using until next year or the year afterwards, but still it's a very, very important one to get through your heads now, and that is that sine squared of theta plus cos squared of theta is equal to 1. Now, in order to do this particular proof here, I'm just going to quickly sketch up a standard right angle triangle. The angle theta can be here, which means that this side length will be the opposite, this side length here will be the adjacent, and this side here will be the hypotenuse. Now, as we said before, we know that sine squared of theta and cos squared of theta are effectively just sine of theta all squared plus cos of theta all squared. Now, sine of theta, we know, is equivalent to O divided by h. So we've got O divided by h all squared. And then cos of theta is equivalent to A divided by h all squared. If we now apply these squares to the quotients, we get O squared over h squared plus A squared over h squared. And because we've got two fractions with the same denominator, we can combine this into a single fraction over h squared, where the numerator will be O squared plus A squared. The question now is, what do we do from here? Well, this is actually where we're going to be using a very, very nifty trick of also using Pythagoras' theorem on this right angle triangle. Because of course, we know through Pythagoras' theorem that this side length squared plus this side length squared is equal to this side length squared. Or in other words, O squared plus A squared is equal to h squared. So we can now replace the O squared plus A squared with another h squared. So we have h squared over h squared, which is of course equal to 1. So we've just proven here that sine squared of theta plus cos squared of theta is equal to 1. Now, even though we won't be using this particular identity until the future, I just want to quickly talk about the implications of this particular identity here. So what this here effectively says is that if we get the sine of an angle, and then we square it, and then add the cos of the angle, and then we square that as well, the result is always 1. And again, this isn't really going to become important until a bit more in the future, but what I want you to quickly do is actually practice proving this from different numerical values. As in, test out things like sine of 20 all squared plus cos of 20 all squared. Try sine of 100 all squared plus cos of 100 all squared. And what you should hopefully find is that no matter what number you use, the answer will always be equal to 1. So just try that with a few more values and convince yourself that this identity here does hold true for any value of theta. Alrighty, with that being said, let us now have a look at two example questions on how we can use these trigonometric ratios. Alright, so what I'm going to do here is I'm first of all going to sketch out this right angle triangle. The reference angle theta is here, the right angle is going to be there. This side has a length of 5, this side has a length of 4, and then this side has a length of 3. And the question very plainly is to write out the values of sine of theta, cos of theta, and tan of theta. Alright, so first things first, let's clearly identify which side is our opposite side, which one's our hypotenuse, and which one is our adjacent. So, the side with length 5 is directly opposite the right angle, so this one here is our hypotenuse. The side with length 4 is directly opposite the angle theta, so this one here is going to be our opposite, which therefore means that the side with length 3 is going to be our adjacent. Now, we of course know that sine of theta is equal to opposite divided by hypotenuse. We know that cos of theta is equal to adjacent over hypotenuse, and then tan of theta is equal to opposite over adjacent. And I've done this by using SOHCAHTOA. Alright, let's start with the sine of theta. So the opposite here is 4, the hypotenuse is 5. So what this here tells us is that sine of theta is equal to 4 over 5. Now, cos of theta, the adjacent is 3, the hypotenuse is 5. So therefore, cos of theta is equal to 3 over 5. And then finally, tan of theta is equal to the opposite, which is 4, divided by the adjacent, which is 3. So therefore, tan of theta is equal to 4 over 3. Let's go through one more example, a slightly more challenging one in this case. Okay, can you already see why this one here is going to be a little bit more challenging? It's because we've been given this side length and this side length, but we do not know what this side length here is. And of course, in order to write the three trigonometric ratios, we need to know all three sides of our right angle triangle. So all you're going to do here, in order to find this missing side length, is we are going to use Pythagoras' theorem. So if I give this side length here a variable, let's just call it x, then we know that x squared will be equal to 5 squared plus 12 squared. Computing 5 squared plus 12 squared gives us 169, which therefore tells us that x is equal to 13. And so therefore, this side length here is going to be 13 units. Then from here, we can clearly identify which side is our hypotenuse, which side is our opposite, and which side is finally the adjacent. So we know that the side with length 13 is going to be our hypotenuse, since it is directly opposite the right angle. The side with length 12 is going to be our opposite, since it is directly opposite the angle theta, which therefore means that the side with length 5 is going to be our adjacent. Now, let's write out our three trigonometric ratios. So we know that sine of theta is equal to O over H, cos of theta is equal to A divided by H, and then tan of theta is equal to O divided by A. Now, let's start off with sine of theta. The opposite is 12, the hypotenuse is 13, so sine of theta is equal to 12 divided by 13. Now, cos of theta, the adjacent is 5, the hypotenuse is 13, so therefore cos of theta is equal to 5 over 13. And then finally, tan of theta is equal to the opposite divided by the adjacent. The opposite here is 12, the adjacent is 5, so therefore tan of theta is equal to 12 over 5. Alrighty, let's summarize what we've learnt today. So in this video, we introduced the three trigonometric functions, sine, cos, and tan. We then delved into the three trigonometric ratios connecting these functions to the sides of a right angled triangle. Sine of theta is equal to opposite over hypotenuse. Cos of theta is equal to the adjacent over the hypotenuse, and then tan of theta is equal to the opposite over the adjacent. To remember these ratios, we can use the acronym SOHCAHTOA. We then use these ratios to prove some important trigonometric identities. Finally, we applied these ideas to some example questions. And that's it for now. See you in the next video.